Hi teacher, my name is Nguyễn Hiếu and today I will present about the V4 replacement algorithm. Okay, let's file. Firstly, we need to file the problem why we need the replacement algorithm. Okay, because the direct mapping algorithm does not require a replacement algorithm because each data block can only be mapped to a unique position in the cache. Therefore, when a new block needs to be brought into the cache and the designed position is already occupied by another block, that block will be replaced without need for decision-making processes. In contrast, in the set associative and fully associative mapping, each line or position in the cache can contain more than one data block. When a new block needs to be brought into the cache and there is no available space, a decision must be made to choose a block for replacement. This requires intelligent decision making to minimize the number of cache misses and maintain the overall performance of the cache. And that's about why we need the replacement algorithm. And next we will file the V4 replacement algorithm. What's the V4 replacement algorithm? V4 replacement algorithm stands for 14 foot hours. Is replacement algorithm commonly used in cache management. In the context of cache, the algorithm determines which cache line or block should be replaced when a new line needs to be brought into the cache and the cache is already full. Okay, we will go to the example to understand deeply about how free-form replacement algorithm work. And over here I have an array of block. This array block like belongs in my memory, and over here we have a column. A column means a set of a cache, a set of cache memory. So in a set we have three lines, and why we have a lot of column over there because what each column will be present the status of the set of cache memory. um, but at this step, so we have a lot of column over there, but it's just one. It's just one set. Okay, we the firstly in set we don't have any data, so block one will be replay the first block in set over here, and block 2 is similar, will be replace the second block over here, and block 5 will be replay the third block over here. So because it don't have the block similar in the cache, so we have the three cache missed over here. I have the red dots is mean one miss, one cache miss. Okay, the next step in the process will take the block 2 for the CPU because block 2 already exists in the set of the cache memory, so easy hit a cache hit, and I have the green dot is mean one cache hit over there. And the block one in cache memory is stay here longest. So when we have a new block, it will be replay the block one, and similar we have a block 3 it does have in cache memory, so it replace the block 1 over here and block 1 is disappear. And the next step is the block 5. Block 5 it already exists in cache memory, so it's here a cache hit, and I have a green dot over here. And the next step is block 6, because block 1 is disappear, so the block 2, so now the block 2 is the block stay in cache memory longest, so the block 6 will be replay block 2 over here. And block 4 is similar, will be replay the block 5 over here. And similar, we have a block 2 and block 3 don't exist in cache memory, so it will be replay the block 3 and block 6 over here. So we have 8 missed, 8 cache miss and 2 cache hits, so the hit rate is 20%. And that is all about the FIFO replacement algorithm. And the next thing is the round robin replacement will be presented by my teammate.
Alright. Hello everyone, my name is Nguyễn Hoàng Hiếu and we're going to present about a round robin algorithm. So let's get into it. Hello everyone, my name is Nguyễn Hoàng Hiếu and I will present to you about round robin algorithm. Well, first of all, what is round robin algorithm? Round robin algorithm is in computing is just a scheduling approach. It will schedule each task. It's like taking turns in a line. Each task gets a fixed time to use resources. This simple method helps prevent resource monopolization, meaning one task won't take too much time to process that can block all the tasks. Alright? So what is time quantum? Well, a time quantum is a shared amount of time given to each process, and it will interrupt the job if it is not completed by then, ensuring that no process or no task can block the whole computer. And what is request queue? A request queue is just an order by which process arrive and are handled. So let's talk I have an example here, so we're going to talk about this example for you to understand fully how round robin works. It's very simple. So first of all, we have 3 things to care about. The first is this table here. This table contains of a lot of information. Our process name, arrival time, and burst time. Arrival time means the time that process will come into the queue. The burst time is the time needed to finish that process. The time unit that we are going to use will be seconds for easy to understand. Time quantum, meaning this is the time that is given to each process to be completed by then. So we have P1 at the arrival time is 0, so it means when we open the program or we do something that this table runs, P1 will be the first one to execute. And because it has the arrival time is 0, it will be the first one to be put into the request queue, as you can actually see here. And now, because we only have one process in the queue, we're going to use that process. And we have this visualization down here. This visualization just for us to understand how it works. So you're gonna see they have these three boxes, and three boxes. There are never four boxes in a row because our time quantum is limited to three. We're gonna have two or one, but we're never gonna have four boxes for one process because time quantum is limited to 3 seconds. So P1 will be put into the visualization here. But as you can actually see, our burst time is 5, meaning we still have 2 more seconds for P1. So P1 is not finished, but the computer will stop P1 process, and it will run again in the future when it's rescheduled. Now 3 seconds has passed, and P2 and P3 already arrived because their arrival time is 1 and 3, which 3 seconds has already passed by P1, meaning P2 and P3 will be put into the queue. And because P1 is not finished yet, P1 will be pushed into the queue again for the future processing. Now let's get into P2. P4, P5 is not in the queue because only 3 seconds has passed, and P4 and P5 need 5 seconds or 6 seconds to arrive, so it's not arrived yet. So P2 will just run, and because burst time of P2 is already 3, which is fit with the time quantum, it's finished. It's already finished, and it will never appear in the queue again. And P3, P2 is done, and we already passed 6 seconds, meaning P4 and P5 will be pushed into the queue because the arrival time has come. And then P3 will be pushed into the visualization here. And because P3 is not done yet, again it has 6 seconds of burst time, but the time quantum of us is only 3, so it has to run again. Now P1 will run because it's the request queue of P1, the P1 turn, and right now the burst time is 0. P1 is finished. Keep doing like that and everything will be finished. As you can actually see, P1 done, P4 will go up. P4 only have burst time of 1, so it will be fit into here. P5 has the burst time of 4, meaning it's not done yet by the time completed, so P5 will be here, and because P5 is not finished, it will be put back into the queue. And then P3 again, and P3 is finished, and then go back to P5. We have 1 second left for the end of the visualization here. So this is round robin. As you can actually see, it's very simple. This simple method fix the problem that one process can block the whole like it can block the whole computer things, so it can block the whole flows of the computer. So like P1 can if we don't use like a round robin algorithm, P1 will take as much time as is needed. So let's say it will take 5 seconds instead of 3. This seems fine in a process that is very fast, but imagine a process that is pretty long, meaning all the process will have to wait for P1, meaning it will give the computer a very low performance, so the user experience won't be good. So they have to use round robin so that each process can have their turn, so the computer can work normally, so it won't block the computer from freezing. So this is round robin, a very simple method but very powerful.
Is Minded Nathan, and I'm going to be walking you through the LFU algorithm. So LFU is an abbreviation of least frequently used. The algorithm is basically to replace the page that has the smallest frequency. So let's take an example. We have a reference string like this, and since it has to do with frequency of the number, I'm gonna write the frequency of the number out in order to keep us on track. So in the first place, the cache is empty, so we just fill it up with these three numbers, and I'm gonna highlight the number whenever it's added to the cache, and I will leave a star right below whenever a cache, a page fault occurs like this. And since we add this number into the cache, we have to increase the frequency of it like this. And now we demand to 2, which is not present in the cache, and so we have to use the least frequently used. In this case, we have 3 number with the same frequency. In this case, we have to apply the FIFO algorithm, which is the first in first out. So the 7 came to the cache first, number 7 came to the cache first, so it will be replaced by 2 like this. And we have a page fault because since 0 is already in the cache, it won't be added to the cache anymore. Moreover, we had to increase the frequency of 0 to 2 like this, and I won't leave a star right below because it's not a page fault, it's the page hit. The reason why we have to increase the frequency of 0 to 2 because when we we knew that 0 is already in the cache because we did a find function, like a get function, so we can tell that it is already in the cache. And because of that, we actually used the 0 one time, so we had to increase the frequency of it. So demand to 3, since look at the frequency, we have 2 numbers with the same frequency, so we have to consider which ones will be replaced. Since and we continue to use the FIFO algorithm in this case. So 1 came to the cache first, came to the cache before 2, so we have to replace 1 by 3 in this case. And it is a page fault, so I will leave a star right below it and demand to 0 again. Since 0 is already in the cache, we just repeat the previous similar steps, and we again increase the frequency of 0 to 3 and demand to 4. So we have 2 numbers with the same frequency, so we consider which one came to the cache first. In this case, it is 0. It is 2. So we have to replace 2 by 4 like this, and it is a page fault, so I leave a star. Thanks. Demand to 2. Again, we have 2 numbers with the same frequency, so we consider which ones came to the cache first. In this case, it is 3, as we can see. So we remove 3 3 and replace it by 2, like this. Leave a star below because this is a page font. And finally 3. Yeah, that's it. That is the least frequently used.
Hello, teacher. And today I'm present about the recently used data. And now I will show you some information about LRU. LRU is a card replacement algorithm. It is designed to replace the least recently used data when the cache memory is full. And the idea of the LRU is the more recently your data will be moved into the patterns, move to the pattern of the list, and push the list recently your data to the top. Will be deleted if the new data is arrived. And you can see here is general example. So it is and move is a button. And now I have an example about list recently used data. So we have list block request here, and suppose the card have a tree line, and the top is the least recently used data, and this button is the most recently used data. And so block number 7 got replaced into the line 0. Number 0 replaced into the line 1, and block number 1 replaced into the line 2. And so when you come into the block number 2, it checks block number 2 is it, it checks block number 2 it will check whether block number 2 is in the card or not. And in this case, block number 2 isn't in the card. And you know when the card is full, it will be delete recently used data. In this case, number 7. It will be put number 2 as the button and push the rest into the top. You have a result here. And number 0, it said number 0 isn't in the card. If I'm sorry. Number and the block number 0. Number 0 isn't have number 0 in the have in the card. And so it will move number 0 into the button and push the rest into the top. And number 3 isn't in the card. So it delete number 1 and push the rest into the button. No, sorry, put number 2 into the button and the rest into the top. And number 0 is similar to here. It will move number 0 into the button and push the rest into the top. The number 4 isn't in the card. So it will delete recent view data in number 2, in the case number 2, and put number 4 into the button. So we have a result here. With number 2 and number 3 is similar in number 4. We have a result here. It deletes number 3, and when come to the block number 3, it delete number 0. We have a result here, and so finish.
The next part, we'll talk about the random.
Hello teacher, welcome to my presentation. I'm Chung from group 7. So now we will talk about the task replacement algorithm, and my part is about the optimal replacement algorithm. So now let's come to the definition. So the optimal replacement is a memory management algorithm whose main goal is to replace paste that are evicted from memory in such a way that the page will not be used for the longest time to come. And the basic idea of the optimal replacement algorithm is to choose based on information about future page usage and which page to keep and which page to replace. So we will come to the example for the optimal replacement algorithm. So now we have a block request here, and we also have the main memory. So in the main memory, we will have the task with 4 lines. Now let's come to the first 4 block requests we have here is the block 2, 3, 4, and 7. So first of all, if you look at the main memory, it's empty, so it's very easy for you to fulfill for the first 4 block requests in the main memory, and we also make sure the first input out to fulfill all this main memory in the task line. So now it's the time for the optimal replacement. Now we come to the first block request is the number 6. So if you want to replace the number 6 in the main memory, we have to consider about the future request. And if we look at the future request, we don't see the block 2 appear in the future request. So the optimal replacement will based on that to replace the block number 2 by the block number 6. So that is the first replacement by the optimal replacement algorithm. And if you continue to the block 3, 4, and 7, we can see that it already appeared in the task file or in the main memory. So we don't need to replace or do anything about the block number 3, 4, and 7. And now, so this is the main memory for the present to after replace the block number 2 with the block number 6. So now we go to the block number 5. So just continue for the old process is we will have to look for the future request information. So if you see that, so the block number 3 and block number 6 are not appear in the future request. So right now we have a problem. So the optimal replacement will based on the block number 3 or the block number 6. But just remember again about the first in first out. It means that what row in first will row out first. So, so right here we can see the block number 3 is row in first. So the block number 3 is also have to row out first to be replaced by the block number 5. And also based on the first input out to do this, and the block number 4 and block number 7 is also already in the task line, so we don't need to replace. And finally we will come to the block number 8. So just continue to our own process. It's based on the first in first out, and number 4 is also the first in, and it's also be the first out and will be replaced by the block number 8. So this is the final result in mid-memory after using optimal replacement. This is just a basic example for the optimal replacement working in the main memory to store data or to replace some requests for the system. So that is the end of the presentation about optimal replacement algorithm. Thanks for listening.